So like I said, this is the classic physics experiment when you have two things drop at the same time. They get shut off horizontally and one that's dropped. And you'll see that they hit. Let's see if I can catch it at the same time. There we go. So they hit at the same time. In the Mythbusters, let's see, where is it? They did the same thing. So they shot not only little pellets, but they actually shot bullets and showed that they hit at the same time. But initially they did the same thing. They had these pinball balls and he dropped one and then he kind of used like a pinball shooter and dropped the other one. And you can see it hit at the same time. But what's more amazing if when I pull this video out, let me see, is when you actually look at the video.
At a provisional.
So if we started from the very beginning, it's a little off, but it's pretty dang close. So if you look right here, you can see it's about almost there. Let me see if I can pause it right on the line. So when it's right on the line, this one's a little bit off. It's about that much off, but it's kind of the same all the way down. So if we go down to the next line. So here it is. It's about the same off. So I'm pretty sure it's just the timing of his mechanism that was off.
For the myth.
But you can see here's at the line, a little bit above. They're practically at the same place at the same time all the way through. So if he kind of just played his video slightly different, it would have fell at the same time. So the big idea here is that when something's being dropped and something's being shot horizontally, they're going to fall at the same exact speed. So, and I'll screenshot these. So what's going on here? So for this one is vertical only. So this ball starts from here and it's dropping all the way down to the ground. Okay, so it's only going this direction and the D and the Y direction. So in this case, vertical only, there is a force acting on it, and that is gravity. And gravity is going to be pulling it down with an acceleration of negative 9.8 meters per second. So if we're going to find anything, so like in my first question I asked, how high is the table if it took the certain amount of time that it dropped? And I believe in the video it said, let me look up my notes, the time it took to drop was 0.402 seconds. So we know gravity is working on this. It's falling. It's going to take 0.402 seconds to fall to the ground. So we could bust out our kinematics, VI, VF, A, T, D, plug in everything we know. A is negative 9.8 meters per second squared. Displacement we don't know, but time we do, 0.402 meters. And it's, oh, not meters, sorry, seconds. And then there's one more thing that we know. He drops the ball. So this is the one example that we didn't do yet. So when he drops the ball, let me get the chat out just so I could see what you guys are asking. That means VI is equal to 0. So now we have 1, 2, 3 of the variables. We could solve for D if we like. So the one without VF is the following. D equals VIT plus 1/2 AT squared. And I personally don't like this problem because it has a square there on the T, so usually it's a polynomial. But in this case, when something's dropped, it's nice because this becomes 0. So it's just D equals 1/2 AT squared. So it's pretty simple. Plug everything that you know in. Square this side and then multiply that by half. Let me get at my calculator. So I'm going to do it in 2 steps. So 1/2 times 9.8 is negative 4.9 meters per second squared. And I'm doing it like this just so you can see that the units do cancel out. So you're just left with meters, which is perfect. Technically it's 2 because you start off with 3 sig figs. But anyway, negative. So this is my displacement down. So the height of the table would be positive 0.792 meters. Okay. Well, why is that significant? Well, that's significant because if we look at the next problem, oops, sorry. If we look at the next problem, and I'll come back to this one to give you guys time. If we look at the next problem, this thing, even though it's falling from the same height. And the cool property is that even though they're falling at the same, they have different horizontal velocities. Because they're falling from the same height, they're going to have the same time it takes to hit the ground. So when you look at the next one, even though, let me move this to the other side. Even though it's falling, it's going to be at the same place, kind of like that video that we saw. Even though this one fell down this way, let me kind of adjust the picture so it matches up. Even though the other one fell down, let's see, that was actually, I could do it. Wait, how did I do the other one? Was it like this? I think it was like this. Pretty close. All right. I don't know what I did. Are they just different sizes? Why isn't it matching up? Oh, it's just different sizes. Shoot. Okay, anyway. Maybe if I cheat like this. There we go. So even though it was like that, this one, even though it's going here, probably around here, then here, then here, then here, here, and here, even though this green one was going straight down, this one was moving at a parabola like this, but at the same points, they're at the same place. So you can see that its vertical motion was exactly the same, even though the horizontal motion was different. Oh. You could just do the doc. That's what you're going to turn in. The slides, I'm going to take screenshots and post it for you so that you always have notes of it. And I'm also doing a screencast so you have a video of it as well. So hopefully that helps. But no, you're not turning in the slide. I'll always post these up. So vertical and horizontal don't affect each other. Well, the cool thing about the Mythbusters is, okay, well, they went extreme. Well, it kind of works when it's like in your physics class, but will it work if you're actually shooting a gun, something that you're shooting super, super fast? So instead of this one, which is kind of slow, they're going to do the same thing with bullets. So they do a couple of tests. First, they make sure that, they can see how far it goes, and we'll kind of come back to this again. But the main idea that they were able to find is once the bullets hit the ground at the same time, we can know these are true. So here are the big ideas for 2D motion. The motion can be broken down into X and Y components. They do not have any effect on it. So from this experiment, from this one to the bullet one, it doesn't matter how fast they shoot it, because this one, I believe they shot it at from a height of 36 inches, and they were able to calculate it, and then it's always going to fall the same no matter what, whether it's dropped or shot forward. So the motion X and Y are different. For us, the horizontal for these problems are always going to be constant velocity. Vertical is always going to be gravity. So when we set these up, it's going to look like this. So vertical motion, which is y-axis, Horizontal will be x-axis. For y, remember it's going to be changing velocity, so it's vi, vf, a, t, d. For horizontal, it's always going to be constant in these projectiles. Now, in real life, there are air resistance, but we're just going to ignore it for our class, so we're going to say it's constant. But in real life, we have air resistance, so technically it's not velocity constant, but it's for most of our world problems, it's going to be velocity constant. Here, we know that negative a 9.8 meters per second squared, and the thing connecting these two is time. The time it takes to hit the ground is the same for both sides. And that's what was shown in that bullet demo that they did. Even though they shot it from 360 feet away, it was still able to hit the ground at the same time. So good so far? X and Y are separate. Y is going to be gravity. X is going to be constant. The key that's going to connect both of them is going to be time. So when we look at these, so the classic physics experiment is that both of these are going to hit the same time. No matter how fast it's moving in the horizontal direction, it's going to hit at the same time as if it was dropped. In the first experiment, it took 0.402 seconds to hit the ground, so we were able to calculate the height from that. We could kind of do number 3 right now, but we're going to do it with the bullet instead. The paintball wasn't perfect because it was round, and a lot of things are happening when the paintball is round, and especially because it was not shot out of a barrel. So if you looked at the paintball, let me see if I could pull up that video real fast.
Go with that. It's a gun. High speed. All right, there we go. It's like fire a paintball gun from this gun and catch a.
So you'll notice, let's see, in another shot you see the barrel somewhere else. Oh, there's the barrel. The barrel is right here, and he took it off. If you never played with paintball guns or even know how rifles work, the reason why rifles are called rifles is because they have rifling inside, or they have these ridges inside the rifle. And as the bullet goes through there, those ridges will make the bullet spin. Paintballs do the same thing with their barrel. It makes the bullet spin, or the ball spin, and as it spins, it's going to have kind of different projectile dynamics. So instead of being like a knuckleball, which is kind of what's happening here with paintball, as it spins, it's going to have some sort of gyroscope kind of effect, even though it's a circular ball, and keep it in a more straight path. When it's shooting out without a barrel, it's going to be more like a knuckleball effect. And if you've ever seen baseball, a knuckleball thrower, that ball is unpredictable. It could kind of go in any direction as you want. And that's kind of what happened without the barrel. Also, the balls aren't perfect. They are like 30-cent balls. So they're not going to have perfect symmetry between them. So you're going to have all these different variations. But a bullet spins, so it helps keep a nice straight path because of that spin. So that's kind of the problem with paintballs versus the bullet, which spins, which keeps it from fluttering around unpredictably. Now, if the .45 caliber was shot from 36 inches, how long did it hit the ground? But the main question I want to answer is, how fast was the bullet traveling? So let's kind of do that together and see how we could solve that problem. Any questions so far? Okay. Let's see if it makes sense, and hopefully I do better this period than I did my other period. The bullet shot out, and they said it hit the ground eventually at 360 feet away. The height that they shot it at was 36 inches. The goal, or the question I want to know, is what was the speed of the bullet horizontally? Out of the pistol. So this is a two-dimension problem. The bullet's going to the left and it's going down at the same time. So we're going to set it up like I did before. We have a vertical, we have a horizontal, we have VI, VF, ATD, DVCT. Now, remember, vertical is gravity, D in the y direction, so that's why gravity is negative 9.8 meters per second squared. Horizontal is constant. That's why I have VC, or constant. So that's not going to change. All right, my velocity is going to be the same the entire time. Like I said before, the key that connects these two is time. So let's fill out as much as we know. From here, we know that the vertical distance is negative 36 inches. And this is 360 feet. So here we have 2 out of 3 that we need. Here we only have 1. There's no way I could figure out these two. But there's one thing that I know here. When it's vertical and we're shooting at a horizontal, kind of back to what we were doing before. Now come back. It doesn't matter what's happening horizontally, or whether it's 0 on the left side or there's movement on the right side. They're both going to fall at the same rate as if it was dropped. All right. So this bullet, even though it's shot out perfectly horizontally, its vertical motion is going to be as if it was dropped. And if it was dropped, whoops, that means VI is 0. So now we have 1, 2, 3 things. So we could solve for time. Once we solve for time, we can move it over here and then solve for velocity constant, which is what we're looking for. Okay, hopefully you caught this. I have both meters per second, or metric system, and I also have inches and feet, which is the American or standard system. So we kind of want to go with meters, or the metric system. So I'm lazy. I don't memorize anything. I apologize. So I just Google it. 360 feet is about 109.72. I'm going to write this down so I don't forget. 100.728. And then 36 inches is 0.9144 meters. Okay, going back to my thing because I'm lazy. So I'm going to convert these. So just make sure all your units are the same. This is negative 9144. And this one is 109.728 meters. 1, 2, 3. We don't have VF. We're looking for T, so the equation you'll use is this one. What's nice is, like I said before, VI is 0. So that's 0. And then you have D equals 1/2 negative 9.8 meters per second squared times time squared, oh, which is what we're looking for. I messed up. We know displacement. And displacement is negative 0.9144. Negative 0.9144 meters divided by negative 4.9 meters per second squared equals t squared. Take the square root of both sides. Sorry. And then let me grab my calculator. Oh. Let me just make sure I did it right. 0.9144. At a time of 0.432, and I'll just keep it, let's see, technically it should be 4.2 because that's my greatest thing right there. Oh, actually I had 4 right there. Okay, so we'll just keep it here. I'm not going to be a big person on sig figs because 4.32 versus 4.31 isn't going to make a big deal for us. So if this time was 0.432 seconds, this one will also be 0.432 seconds. Now you have two things and you can solve for it. So D equals VCT, 109.728 equals VC times 0.432 seconds. And I get a velocity of 254 meters per second. So that's how fast the bullet is coming out of the gun. So hopefully that kind of gives you a good example of how a 2D motion works. I did a lot today. I did about 3 or 4 days worth of materials of practice and like doing demos in class, and 1 day just because of our new format here. So it is a lot to absorb. Hopefully the video kind of break it down, but the main idea is the vertical is separate from the horizontal. The only two that's keeping them together is the time. The vertical is what we did before, VI, VF, ATD, as if something dropped. So VI is 0, A is negative 9.8, and your displacement is how high up you shot your arrow, bullet, ping pong ball, whatever. The horizontal distance is connected by just the time.
I have a question, Mr. Tang.
Sure. What's up?
If you factor in air resistance, will that change the result in any way?
It would. So if you factor in air resistance, then our horizontal, this right here, will no longer be constant. For a bullet, it's very slim because it is aerodynamic. You know, bullet is usually pointed at the tip. If it was like a musket, you know, since it's a ball, it might be different. If you put a backspin on that musket, then it'll kind of rise. So it's kind of like tennis. You could put a top spin and then it'll dive on you. If you put a backspin, it will go up on you. Same thing with golf. You could put a top spin on it and it'll dive on you. Backspin, it'll go up. But for bullets, since it's pointed and it's kind of, its spin is in the axis is a little bit different. It's not going up or down. The spin is left and right, so it doesn't affect its up and down motion. But yeah, if there is air resistance, it will slow down enough. But for a bullet, it's not going fast enough to really see a difference. You'll see a big difference if like a bullet is shot into water, right? Big caliber bullets, when they're shot into water, just disintegrate because they're going too fast. The pressure of the water just breaks them apart. But a smaller caliber bullet could actually go through water. So if you ever watch like a war movie, like Saving Private Ryan, if you dive underwater, they're safe because all those high caliber bullets can't get into the water. It's actually the low caliber ones that could get in. But yeah, that requires calculus. So for us, we're just going to assume no air resistance.
But with the air resistance, the times would still be the same, right?
The time will be the same, but the displacement in the x direction will be shorter. Should be shorter. Unless the bullet had
Right.
lift. Which it shouldn't. But a golf ball kind of does. So it really depends on the object that it's moving. So a golf ball, since it has a backspin, I forgot what the name of the principle is, but it'll have a lift, just like a baseball. If you can make a baseball go up or down based on the pitch you throw, or left and right too. Any other questions?
Yeah. So would you say that the projectile having less air resistance would be a way to improve this test?
Yes. So if you really want to be super accurate, if we go back to that, so there is air resistance, but they were in a building, so there was no wind, but there's still some air resistance. So if they wanted this to be a perfect experiment, they'll do this in a vacuum, because then the horizontal will be constant. So here technically it does slow down a bit, but if it was in a vacuum, it will be perfect.
Got it. Thank you.